Good afternoon, everybody. Welcome to this final event of the Curabone project. I would like to thank everyone for attending this webinar, the biomechanics master students of the Universities of Zaragoza and CAU Leuven, and all the attendees who have been registered or are following the event live on YouTube. My name is José Manuel García Aznar. I'm the coordinator of Curabone, an industrial doctorate funded by the European Union, which started in 2017 and will soon end after 4 years. We want this event to show and present the results of the project, above all to offer a space for the early stage researchers who have been the soul of the project, to tell us about their research and their personal experience as Marie Curie students. First of all, we will watch a short video summarizing the main goals of Curabone and the training of Curabone and the different individual research projects of all the students. After the video, María Ángeles Pérez from the University of Zaragoza, training coordinator of the project, will say a few words highlighting the academic dimension of Curabone. Then we will give the floor to the research students presenting all the different research work. Finally, Can Engelborg, research manager at Materialize, will speak about the importance of scientific research and innovation for industry and will close the event. Of course, if you have any question or comment to their presentations, you can use questions and answers in Zoom and vote the best question or the chat in YouTube. At the end of all the presentation, we will discuss this question. So now we are going to start. Let's start with the video.
When bones are fractured or injured, our body has a fantastic ability to rebuild the damaged bone as if the break had never happened. However, certain situations, such as cancer removal, traumatic accidents, and genetic defects, exceed the body's natural healing capacity. Traditional solutions include standardized metal implants, animal bones, or pieces of human donor bone. Nevertheless, none of these is optimal as they can cause infections or can lead to rejection by the patient's immune system, and they cannot perform most of the functions of healthy bones. The predictability of the surgical outcome is something that surgeons appreciate more than anything else. Therefore, a patient-specific approach can often be much more suitable than traditional standard solutions.
Curabone is a research project where we propose patient-specific treatments in different orthopedic problems. We are developing a multiscale strategy for modeling the musculoskeletal system that describes from the biomechanics of the whole organ to the mechanobiological processes at the cell level.
All this would be impossible without the joint effort of all the members of the team, in which each one is analysing bone functionality at different length scales. David is working in musculoskeletal modelling to understand how muscles drive our bones. Hence, he aims to predict patient satisfaction after a bone implant, mainly focusing on total knee replacement.
In this part of the Curabone project, we work on the development of a pre-planning tool for total knee osteoplasty surgery. I use musculoskeletal modeling and artificial intelligence to research the interaction between pre- and post-operation kinematics, taking into account contact forces, muscle forces, soft tissues, and implant position as well. I further researched correlations between patient-reported outcomes and biomechanical measures.
Jonathan works on the fixing optimization of a bone implant, primarily focusing on shoulder implants. He aims to reduce the movement between the bone and the prosthesis to increase the osseointegration and improve the stability of the implant.
My PhD project focuses on the design optimization of a 3D printed custom implant for reverse shoulder arthroplasty. To do that, I will use both computational approach, like for example finite element model and statistical shape model, and experimental approach to improve the current pre-planning phase. In particular, the main goal is to offer guidelines to the surgeons regarding, for example, the number of screws to use during surgeries, which type of screws to use, and in which position insert those screws to have a better implant stability. In the end, this will allow the patient to benefit from a better surgical outcome.
Antoine is studying the bone healing process that occurs after a bone fracture, with a focus on the design of fixation plates in the mandible. He aims to predict the best outcome for patients after bone surgery.
My project focuses on developing bioresorbable and patient-specific bone plates for facial applications.
I use finite element modeling to simulate the healing process of the bone as well as the biodegradation of the plates after surgery. These tools can be used to optimize the plate design in order to get the best outcome for the patient.
Gabriele uses the latest advances in microfluidics-based 3D culture to study the role of mechanical stimulus in bone formation for bone tissue engineering applications. In fact, with the newest digital technologies, he aims to predict the integration of titanium scaffolds in bone tissue.
The effect of mechanical stimulation on bone formation depends on both the individual response of the patient and scaffold mechanics. So thanks to the Curabone project, I'm using both in vitro and in silico models to enhance the osseointegration of patient-specific implants.
Simon aims to design and fabricate novel biodegradable scaffolds to improve bone regeneration at the cellular level.
The main idea of my project is to use new devices that we call bioreactor to reproduce the physiological condition to test the degradation process of our materials. Thanks to these new devices, we can drive the degradation process and then we can create digital tools to predict the long-term behavior of the degradation.
Students who participate in Curabone receive training in both industry and academia. Thanks to this project, young researchers from different countries working all over Europe are being supported. The University of Zaragoza recruited 2 of them, and Materialize, the industrial partner, hired the other 3.
Curabone is a project to develop individual-specific treatments for bone injuries at different length scales, from cells to our bones and muscles. Knee replacement, shoulder implants, mandible plates and bone scaffolds are different kinds of implants that have been analyzed. After Curabone, ESR researchers will continue their career and bring research results and competences into society as future leaders.
This project is an industrial doctorate funded by the European Commission. We would like to thank the rest of companies that host our students during the development of the project. Anybody from Denmark, Robert Jones and Agnes Hahn Orthopedic Hospital from United Kingdom, and Hospital Lozano Blesa from Spain. In addition, other academic institutions have participated in the project, the National University of Ireland in Galway and KU Leuven in Belgium.
If you want to know more about our work, you can visit our website or follow us on Twitter, Facebook or LinkedIn.
Thank you very much. Now we are going to start with the presentations. In the first term is María Ángeles, who is going to present.
So thank you very much, Manu. Curabone has been a European industrial doctorate that is one of the modalities we can find in the innovative training networks. Our industrial partner, Materialise, has had a very important leading role, but also the presence of the academia, mainly the University of Zaragoza, but also as coordinators, but also the collaboration of KU Leuven and the National University of Ireland in Galway has been essential for the successful development of Curabone. The role of academia has been to provide scientific training to reach Curabone project goals. The academia, the University of Zaragoza in this case, we have very important background on the different topics of the project. In fact, our background has been the pillars of most of the new technologies that has been here developed. Additionally, we have had a very well-known scientists as visiting researchers that have shared with us and with all the team and with the scientific community their valuable knowledge. I would like to especially mention Professor van der Sloten and Van Lente from KU Leuven, but also Professor Luca Cristofolini from University of Bologna or Professor Gwen Reilly from University of Sheffield. But also not only we have had visiting researchers from Europe, but also from the United States as Scott Hollister from Georgia Technology Institute. And finally, in summary, I would like to say that Curabone Academy have covered high training activities and have offered a high level of international networking.
Thank you very much, María Ángeles. And now is the tour for the students. So in the first place, David, please.
Thank you, Manu. Let me start by sharing my screen, and I will immediately start with my presentation. Okay, good afternoon, everyone. My name is David Leandro, as Manu said, and I have the pleasure to be the first early-stage researcher of the Curabone project to share his work in this webinar. I would like to start this presentation talking about my experience. I started my work in this project later than my colleagues in November 2019, with my main location being in Leuven in Belgium, at the headquarters of Materialise. After my initial training here, I did a short research stay at Aalborg University in Denmark, which biomechanics group is highly specialized in musculoskeletal modeling. Once I returned to Leuven, the pandemic started, which restricted the rest of my experience to online seminars and meetings. My work in this innovative training network has been focused on the development of computer-assisted patient-specific tools for total knee arthroplasty. Total knee arthroplasty, abbreviated TKA, is a procedure often performed as last resort to alleviate pain and restore function in severe knee osteoarthritis cases. In TKA, the damaged joint is replaced with a prosthetic femoral and tibial metal implants and a tibial plastic insert. Typically, TKA is performed following a mechanical alignment, which aims for a neutral hip, knee, and ankle position. So to position the hip, knee, and ankle in a straight line, thereby correcting for any varus or valgus that was originally present in the patient. However, it has been shown that mechanical alignment is not natural in most healthy knees and might therefore affect the natural kinetics of tissue strains and kinematics, which could explain the relatively large dissatisfaction rates of up to 20%. Therefore, in the first part of my project, we wanted to research whether it is possible to restore native knee function with standard QC retaining implants after TKA by modifying the implant position and therefore the leg alignment. For this, our goal was to develop a workflow that will allow us to modify the implant position as wanted to achieve a desired knee function. Some results from this part of the project were published as an abstract for the computer-assisted orthopedic surgery meeting of last year. All my research and the developed tool is based on patient-specific musculoskeletal models, which are in turn based on medical images, in this case, in magnetic resonance images. In these images, the femur, tibia, patella, and fibula are segmented, which are used to adapt a musculoskeletal model template, including muscles, ligament, bones, and contact geometries. And it is with this musculoskeletal model that we can perform a force-dependent kinematic simulations, which allows us to estimate tibiofemoral kinematics, taking into account muscle, ligament, contact forces, together with patient-specific geometries. Although constructing patient-specific musculoskeletal models is a time-consuming process that requires selecting multiple bony landmarks and ligament attachments on the subject's segmented bones. Therefore, creating large batches of patient-specific models manually is quite unfeasible. So we decided to create a statistical shape model to predict the position of these necessary landmarks. With this method, we only had to apply our SSM to the specific patient geometry and use the SSM output to shape the musculoskeletal model template, reducing by more than 4 times the time required to build a musculoskeletal model. With the musculoskeletal models, we were able to develop a workflow to find an optimal implant alignment that will restore native joint behavior while taking into account soft tissues. In the research that I showed today, the goal was to find an implant position that reproduces the native knee motion with off-the-shelf with standard implants. As previous research showed that a more normal gait pattern results in improved patient outcome. However, the platform also allows for other planning strategies as well, such as to optimize to ligament elongations. In the workflow itself, we first simulate the movement with the native knee. Then we include the prosthesis to substitute the joint contact and simulate again, where we can already appreciate the difference between pre- and post-operative joint behavior. Then we train an artificial neural network with hundreds of simulations where we randomly change the femoral and tibial implant position within a range. Finally, we use the results of the artificial neural network to find the implant position with the least squares difference between native and TKA output, which we term the optimized plan or the dynamic alignment. The result from this workflow were applied to 4 specimens, and it's the results published in the previous abstract that I mentioned. I will quickly switch to my second project, which also involves around musculoskeletal models of the knee. But in this case, we work with patients who underwent a TKA and filled patient-reported outcomes, which are questionnaires to measure patient satisfaction. Patient-reported outcomes that were filled before surgery and 3 months, 1 year, and 2 years post-operation. In this second project, our goal was to relate model predictions to patient satisfaction scores, which could potentially allow us to predict patient satisfaction after TKA based on the patient's post-operative knee behavior. Using the developed statistical shape model, we managed to create multiple patient-specific musculoskeletal models efficiently, which opened the possibility to estimate knee kinematics of multiple patients. Predictions that we can already use for our goal to relate model outputs with preoperative patient satisfaction. Afterwards, we only have to substitute the native joint contact with the prosthesis and simulate again. Now we are able to compare pre- and post-operative kinematics and attempt to relate these model outputs with the patient-reported outcomes. In terms of publications, I am currently writing a paper from the first project explaining the dynamic alignment tool. A second paper will also be written derived from the findings of the second study, once I have the results. Afterwards, we could write a third paper from the combination of the pre-planning tool applied to patients, which will conclude my training in the innovative training network and hopefully end up with my PhD. That was all I had to share today. But if you have any question, remember to write them in the question and answer dialogue here in Zoom, or feel free to drop me an email. Thanks for your attention. I'll give the word now back to Manu.
Thank you very much, David. Now it's the tour of Jonathan.
Thanks, Manu. I will share my screen. So, welcome everyone, and I'm Jonathan, and I'm the second ESR of the Curabone team. So we will switch now from Spain to Italy, because that's where I come from. To give you a bit of a background, I studied biomedical engineering at the University of Bologna, both the bachelor and the master. And then I moved for my master thesis to Reykjavik in Iceland for looking for a new challenge. You can imagine it was quite a big step, but there I really had the possibility to work in an international research environment and work closely with surgeons. I focus mainly on planning for hip arthroplasty. And it's there where I started to think about the possibility of a research career. And it's after that I actually joined the Curabone team and the Curabone project, and that's how I ended up here in front of you. I was hired as David by Materialize, which is the industrial partner of Curabone, and these slides just represent, I think, one of the strengths of the Curabone, which is putting together academic and industrial partners, academic KU11 and Zaragoza, where I also spent some months, and Materialize, the industrial partner. So what was the focus of my project? I mainly focus on shoulder, and in particularly to develop a new tool to personalize the approach to shoulder arthroplasty. So shoulder arthroplasty is a procedure to replace a pathological shoulder joint with an artificial one, and we can also, in this case, opt for a more personalized approach. And we hear a lot about personalized medicine. Here I try to narrow it down to my project and to my topic. So we normally start from patient-specific data, clinical images and bone models, and those data are input for planning software in which the surgeon basically can decide between different implant position and design and plan the surgery before going to the OR. Once the surgeon is happy with the approved plan, then this plan can be transferred to the OR through different technology and different tools. You can see some of them in the slides. But you can also opt for a more specialized approach. In particular, when there are large defects at the scapula level, standard implants are not more enough, so they need to use custom implants, which are printed and built specifically for those patients. Now, there is a lot of technology involved. I focus just on two phases of this workflow, in particular the design phase and the planning phase. And I try to develop computer-aided tools to improve this personalized approach and to potentially improve the functional outcome for patients. I defined 3 projects in which I use different computer-aided tools to reach my goal. In the first one, I developed a finite element workflow to improve the current design of custom shoulder implants. So here, the main focus is the fixation of the custom implants. There are already large defects, so there is not a lot of bone stock left. We need an implant that is quite stable, but we cannot perform mechanical tests because, as I told you, there is a lot of each design is unique for each patient. On the contrary, we can use finite element model to predict this initial stability by focusing on micromotion estimation, which are essential for allowing bone ingrowth and allowing secondary fixation. That's what I did in an automated workflow that now can be used by design engineer to compare different design and then pick the one that is the most suitable in terms of fixation. So in this way, we expect a more straightforward design of the implant with also higher benefits for the patient. In a second project, I use statistical shape technology to create a novel tool that integrates bone quality information, mainly cortical thickness, and bone shape information together. We first created an algorithm to automatically estimate the cortical thickness, and then I integrate this information through SSM. In this way, we have a tool to generate a virtual population in which the variation of bone shape and bone quality is described, as you can see in the slides. And this tool actually represents an alternative to cadaver lab to infer measurement for the design of implants. Potentially, an industrial partner or a customer can use this virtual population to virtually implant the design on the virtual population and see if its shape, it's congruent, fits the variation of the population, or even if the screws they insert in the cortical thickness, which is the stronger bone of the scapula. In the last project, I moved to the planning phase, and in particularly, I try to add new features to the current preoperative planning software by focusing on soft tissue. As we saw for knee, also for shoulder, they have an impact on the outcome of the surgery. And in particularly with this project, I developed an automated workflow to estimate muscle elongation during the preoperative planning. I use SSM to do this estimation and validated this approach in order to give accurate measurement to the surgeons. And in this way, surgeons during the preoperative planning can design and can do clinical decision guided by this muscle elongation tool, and hopefully have a better plan and a better outcome for the patient. As main outcome of my research, I could also have an impact on the industrial side. And in fact, part of the algorithm that I developed are currently included in the software of Materialize. You can see some example in the slides. On the right, in particular, there is a mock-up of the muscle elongation tool that will be used now by the surgeon to plan the shoulder arthroplasty. That's the view that they will see, and they will also see some analysis measurement that they can use during the planning. Together with the industrial impact, there was also a scientific impact in terms of publication. I published the main results of my 3 projects on a research article. I also, together with some colleagues of the Curabone project, published papers. And finally, on the 2nd of February, so literally 1 week ago, I was awarded with my PhD, which was also a really nice and major achievement. But it's not all work and research. There was a lot more during the 3 years of Curabone, and dissemination, presentation like this one during webinar. I could travel to Canada, to Ireland to present my work. So, and yeah, I've been in contact with other research team, get their knowledge and their know-how. So was really interesting and really good for my own career. And probably are you wondering what I'm doing now? Curabone gives you really a lot of skill, and I think the right skill to pick your own career. And in my case, I joined Materialize, and I will be research coordinator for shoulder, continue to work on my research, but also focusing more on the long-term view that we have. We want to impose to shoulder innovation in Materialize. And with this, I want to conclude, and thank you for the attention. And if there are a question, I will answer them. Thank you.
Thank you very much, Jonathan. Now is the tour of Antoine.
Yes, thank you, Manu. I'm going to share my screen just a bit. All right. So, good afternoon, everybody. My name is Antoine. I'm the 3rd Curabone ESR. So I will start by briefly present myself and then talk about my research within Curabone.
So I come from France. I studied at the University of Lorraine between 2018 and 2020. I finished actually in June of last year. I did my master's thesis internship at the University of Zaragoza. That's where I got my first contact with the Curabone project. I worked with Gabriele on research on the bone ingrowth model that he will explain later. And finally, well, at the end of my master's thesis, Curabone was looking for someone, and it was a good opportunity. So here I am now, and I'm working well at Materialize in Leuven, so since August. So my research topic is entitled Feasibility of Bioresorbable Bone Plate for Orthodontic Surgery. So the first question is, what is orthodontic surgery? It consists in realigning the jaws when often it's because of a congenital defect. It's both for aesthetic and functional purposes. For instance, the masticatory force can be quite low, and it can, of course, have a negative impact on the patient's quality of life. So one of the solutions most used nowadays is virtual planning. So it consists in doing the segmentation of the patient's skull from a CT scan. And then the surgeon and the clinical engineer have a planning session. They define which are the osteotomy planes, so that you can see here in the chin, here in the maxilla, and here in the mandible on both sides, actually. Once they define, cutting guides are generated. And then decide where the final position of those bone segments should be. And patient-specific plates are generated. What I'm showing you here is a solution that Materialize is offering to surgeons. So the current, let's say in the current solution, titanium plates are used. So it has a very good biocompatibility, but the problem, it doesn't degrade. So either surgery is needed to remove the plate, or the implant is staying permanently in the patient's body, which can be a problem. It can increase the risk of infection, or it can lead to stress shielding because titanium is much stiffer than bone. So bone could lose density, and of course, we want to avoid that. So a possible solution is to use biodegradable materials such as magnesium and PCl. So in my research, I have focused on magnesium. The problem is we need to predict in some way the behavior of the plates over time. That's why using an in silico model is a way to get a preliminary answer to this problematic. So to do this, I combined 3 elements. So first, a finite element model based on a clinical case. Then I incorporated a biodegradation algorithm for the plates and a bone healing algorithm in the fracture gaps. Because I want to predict the performance of the plate and answer the question, will the plate hold the load and the bone segment together during the healing period? So to create this finite element model, as I mentioned earlier, I used the geometry based on a clinical case. The masticatory loads were applied using forces in muscle insertions that you can see here in purple. And then the load is in fact increasing over time because a patient in the recovery phase can't bite at full force because also the soft tissues are healing. And then a mechano-driven bone healing algorithm is applied in the fracture gaps. So the fracture gaps are what's here in red. It corresponds to the osteotomy plane, actually.
In this work, I focused on the mandible and not on the maxilla or the chin because it's the load-bearing application. I also had to use a thicker plate design for two main reasons. First, the elasticity modulus of magnesium is almost 3 times inferior than the modulus of titanium. And also the loss of mass during the corrosion means that we need more mass, in fact, if we're going to lose mass. So yeah, let's come to the biodegradation of magnesium. So I used an algorithm implemented, yes, as I said, in the finite element model. And you can see here what the result is over time, what we get numerically. And it's important to mention that this model was calibrated with in vitro corrosion experiments to get a result as close as possible to reality. Of course, it will still be an estimation, but it will be a better estimation. Concerning the results of what such a model can give, so we define 3 metrics to estimate the evolution of the system over time. So first, you can see here in yellow, it's the percentage of bone healing. 100% means that the properties in the gap are similar to the neighboring bone. Then the mass loss that happened in the plates. And what is very interesting for us is the maximum stress also in the plates, because we don't want this stress to be higher than the yield strength of the material, which in the case of magnesium is around 200 megapascals. Concerning the scientific output of this work, or in general in the Curabone project, so I've been the co-author of 1 research paper during my master's thesis. So, as I said earlier, Gabriele will develop this topic later. And I also have 1 manuscript in preparation for the work I showed you just before. Well, because of the COVID situation, I couldn't do any conference or dissemination, which is a shame, but we all have to deal with it currently. But this was a very positive experience for research. So I'm sure that I want to continue as a researcher, and in the future, I want, let's say, to do a full PhD. So that was all for me. Thank you for your attention. Don't hesitate to ask questions. I'll give the word back to Manu.
Thank you very much, Antoine, for your presentation. Now is the tour of Simone.
Thank you, Manu. I'm going to share my screen. Okay. Hello, everyone. I want to thank you for watching my presentation at the final event of Curabone. So I want to shortly introduce myself. My name is Simone Russo, and I'm the second Italian of the Curabone project, and I'm from Vittoria. It's a small city in Sicily. My background is in biomedical engineering, and I took my bachelor degree at the University of Pisa and my master degree at the Politecnico of Milan. Here you can see my working experience before joining the Curabone project. In the first one, I was a student intern at the research center Piaggio in Pisa, where I was working on developing a membrane bioreactor. This is a smart device that can replicate the physiological condition occurring in an interface tissue, such as small intestine, kidney, or lung. In my second working experience, I was a visiting research assistant at the UCL Institute of Child Health in London, where I was working with the decellularization and recellularization of organs. So basically, what we were doing was to harvest organs from animals, take off all the animals' cells, and then replace these cells with the humans' ones. Then in my last experience before joining the Curabone project, I was a researcher at the Orthopedic Institute Galeazzi in Milan. And here I was working to create in vitro a functional cartilage. So basically why I chose to join a PhD in a Marie Curie project, and why I think, and now I'm talking to the student, why I think you should evaluate this opportunity. There are many reasons, and here you can just see a few of them, and the most important for me. The first one is the topic. It's really hard to get this kind of funding. So the project that obtained this funding must be innovative, challenging, and really interesting. The second reason is places. So basically you must move from your home country in at least one or usually two new countries. In this way, you will discover new cultures and new places. The third reason is travels. Within the project, you will be able to travel a lot to different places because of congress, school meetings on various activities. And in this way, is also in this case, it's also included the fourth reason, the trainings, because many activities during the project are intended to train you as a scientist and researcher, and to improve both your soft and hard skill. So I want to talk a bit about my PhD. As Manu already said, we are an European industrial doctorate. It means that I had to spend half of my PhD time in academia and half of the time in a non-academia partner. The two partners involved are the University of Zaragoza in Spain and Materialize in Belgium. It is really nice to have the opportunity to see two different approaches to research, academic and industrial. And in this way, after this experience, I can say that what kind of research I like most and what kind of research way I want to continue. So just shortly about my project, I'm working on biodegradable materials for bone tissue engineering applications. And the main idea is to study materials that can repair a small bone defect and over the time disappear and are replaced by the bone itself. And I used a combined approach, computational and experimental, so in silico and in vitro. I followed all the steps of my project, so starting from commercially available polymers, PCL and PLGA, we created the filament that then we use with a 3D printer to create our sample that we then tested. And in order to test our sample,
we look at two different conditions. So we want to test our sample under static and perfusion condition. And in order to do this, I designed a new devices, a bioreactor that allowed us to control the perfusion on our samples. And here you can just see an example of the result that I obtained, in which I compare the weight loss of the sample in the experimental result in vitro and with the in silico, so the computational prediction. However, what I want to stress more is that Marie Curie PhD is not only a research science, but you get a more complex experience that cover different aspects. And here I'm just summarizing these three: so networking, dissemination, and formation. You basically develop your own network because you will meet scientists and people that can improve your research. And thanks to the dissemination, you can discuss your research with people that are the best in that field, and maybe you can also improve your research work. And then the formation, because you will have the opportunity to attend many winter school, summer school, or courses that are focused on your improvement, so to improve your skill. And here you can just see a map of the main activities that on the main place where I was doing my PhD, of course, because before the coronavirus. So basically, the message that I want to deliver mainly to the student is that indeed the PhD, the Marie Curie PhD is during the PhD you will do science, but most important, you will have many experience. You will live many experience. So you will meet people. You will make new friends. You will face up a challenge, but you will, of course, you will have a lot of funny moments. So that's more or less my presentation. I want to thank you for attending my presentation. If you have any question about my work or general question about Marie Curie PhD, feel free to contact me. But I also want to thank all the people that has been involved in this project, since this is our final event, and I want to tell them that it was a pleasure to share this journey with all of them. So thank you.
Thank you very much, Simone. Thank you. So now is turn for Gabriele.
Yes, okay, here I am. Okay, great. Good afternoon, everyone. And yeah, to be honest, I really didn't expect the final event of the Curabone project to be an online event. But yes, here we are. I'm actually glad, at least glad, that there are several students attending it who might be interested in an European industrial doctorate, in starting a European industrial doctorate. So I will just briefly tell you my experience in the Curabone project, how it started and what I really learned from it. And so let's start from as an introduction of what I was when I started the Curabone project. Like all other, the majority of the early stage researchers in the Curabone project, I'm also Italian. I'm coming from Sicily. And my backgrounds are in mechanical engineering as a bachelor, then a master in biomedical engineering. And during my thesis, I really fell in love with the field of tissue engineering. So after my studies, I really decided and I was sure that I wanted to do a PhD on this topic. So when I was looking at different PhD opportunities, yeah, here we are. I would really recommend, this website, because I found this website that was a wonderful discovery for me. And that's how I found the Curabone project, actually. So for any students actually might be interested in doing a PhD abroad in Europe, this is a wonderful resource, because all European projects that has PhD, that are funding PhD, they need to upload the vacancy in this website. So please just have a look at it. It's very useful. But yeah, so if you're looking for a PhD in Europe, just go there. And indeed, Europe has been the key word for my Curabone project. Because if I look back at these 3 years, and I lived in 4 different European countries. I don't know how many times I changed apartment. That was crazy. But yeah, I think I really took the most of this experience, starting from Spain. That was my home institution. I then moved to Ireland, to the National University of Ireland in Galway. I went to Oswestry in the Robert Jones and Agnes Hunt Orthopedic Hospital. And then I finally ended up in Leuven, where I spent the second half of my PhD between KU Leuven and Materialize. And I mean, as you could see from the rest of the presentations of my colleagues, the topic, of course, of our project is focused on 3D printing applications of orthopedic implants developed by Materialize company. But if we go a little bit more into the details of my work, I was focusing more on the bone regeneration process that is associated to these orthopedic implants. Of course, when we talk about bone regeneration, we don't talk about implants anymore, but we are more focused on, we call them scaffolds, because they are actively guiding the bone regeneration process. But of course, I was studying this process in a patient-specific context, as the orthopedic implants produced by Materialize are. So I divided my research in 2 main topics. The first one focuses on studying the scaffold mechanics, the role of scaffold mechanics, while the second topic models the individual response in bone-on-chip devices. So I used, from one side, the computational technology, and I will show you now just the main results of both works. So the computational technology to study the role of scaffold mechanics in bone regeneration, and the other one I used the microfluidic technology to model the patient-specific response, right? So for the first research field, I developed a mechano-driven model of bone regeneration in porous 3D printed porous scaffolds. So I assumed that the bone regeneration process could be explained by a model that was purely based on mechanical stimulation and its dynamic change over time. And we saw that such a model could actually predict variations in bone ingrowth distributions when those porous scaffolds were inserted in different locations of the tibia or the femur. And we actually validated and calibrated these models with in vivo data that Materialize had performed in the past. And we could actually observe that exactly when the scaffold was inserted more in a epiphyseal or diaphyseal location, the bone ingrowth distribution was totally changing, and the mechanics could really explain this variation. Of course, it doesn't mean that the mechanics is the only factor affecting it, leading to these results. But of course, we could use this tool to predict variations in bone ingrowth distribution. Moreover, we could also provide a mechanical interpretation why we had, at least it was observed, limited bone ingrowth formation, bone ingrowth inside the core of the scaffold. So these are the main results of the computational work of the first study I did in the Curabone project. The other study, and as I said before, we are talking about patient-specific applications. So it means that the patient itself might have a really unique role in the final outcome, in the final regenerative outcome of the scaffold. So what we needed to do is actually to model this, to develop an in vitro technology where we could culture cells isolated from individual donors. And that's why then we use the microfluidic technology, where you could actually create in vitro complex 3D microenvironment where you culture cells isolated from individual patients. So in this study, we proved that we could use this technology to culture primary human osteoblasts. In this case, we isolated them from 2 different donors. We cultured them in a 3D microenvironment with cells embedded in a collagen hydrogel in these devices. And then we assessed their osteogenic activity. And indeed, we observed that we could induce their differentiation towards osteocytes, especially when they were cultured at higher cell ceiling densities. And we evaluated then this differentiation by means of morphological parameters like the increase in primary protrusion length over time, the proliferation that was actually interrupted when those cells were differentiating, the alkaline phosphatase also activity, and the synthesis of osteocytic marker. So at the end, we developed this bone on chip where we can isolate, we can culture individual cells, and we can assess then the ability to form novel bone tissue in different environments and under different mechanical chemical stimuli. So of course, I'm aware that I wouldn't have been able to reach any of these results without the great network of researchers that I met during the Curabone project. As I said before, I've been in quite several countries in Europe. I met researchers with totally different backgrounds, and it was fantastic, really, from both a human and a professional point of view. But of course, besides meeting people in a research context, of course, as Simone said, I enjoyed a lot also disseminating my results in conferences, in winter schools. But if I really need to pick one of the most special dissemination activity, I will never forget the time when Simone and I went to primary school presenting our work. And indeed, probably it turned out to be much more difficult than what I believed, explaining to kids how we aim to really heal bone using a computer. But anyway, if we focus then more on scientific output and something more scientifically relevant, I ended up after these 3 years with 4 manuscripts, 2 research papers and 2 literature reviews. Just the papers were already being published. The research papers have already been published. The reviews are still in preparation and revision. But now, of course, I mean, after wrapping up the research, I'm of course finalizing also the PhD thesis. Meanwhile, I'm keeping doing research here at KU Leuven. So yes, I'm almost done also on that side, hopefully. So yes, if I really look back what the Curabone project meant to me, I would really recommend it to anyone who is looking for a PhD experience. I would recommend it really to everyone, because to me, it's been really the right combination of different research experience, but also in other out of research experience. So I could really learn a lot of transferable competencies in the way I really communicate, and also regarding data analysis, image processing, and computational modeling. So really this brings me to the end of my presentation. I give the word back to Manu, and I'm sorry for the background noise, actually will remove.
Thank you very much, Gabriele, for the nice presentation. Thank you very much, all of you, for this time, for working together. It was a pleasure to work with you. Okay, so now finally it's a pleasure for me to present Koen Engelborg, that he is the research manager at Materialize.
Thank you, Manu. I will share my screen. I hope you see my presentation. So as a few closing remarks of this event and of the whole Curabone project, I want to highlight a bit the importance of this type of project and of Curabone in particular for Materialize and for the biomedical industry. And I want to do it with this example. So this shows some data from standard hip implants. We know from hip implants that about 10 to 15% actually fail during the whole lifetime of the patient. And of those who get a revision, so an implant replacement, actually 15% fail on very short term. And of all the revisions that are done, 30%, so about 1/3, are actually re-revisions. What happens is that due to the bone loss, and due to the fact that the implants have to be changed and replaced, that the failure rate roughly multiplies by 3 each time. So these patients go into a more bad situation every time, and some patients go into 4 or 5 revision surgeries, or end up being completely losing mobility and having to stay in a wheelchair. Now, what we did is we changed this situation completely by having a fully optimized patient-specific implant. So the bone loss is replaced by a fully porous metal part of the implant. The screw positions are optimized with simulation, with finite element simulation. And in this way, we can actually change this negative spiral for these patients into a situation where we have proven 98% of implant survival and 100% patient satisfaction and mobile patients. So this is only possible because these implants are patient-specific and are fully optimized using simulation. And that's what we as Materialise really believe in, that personalization of implants and optimization of implants and of planning can actually lead to more predictable treatment, and that this should be accessible to a much larger number of patients. And in the end, also should be economically more viable, because 1 surgery is better than 4 or 5 surgeries. Now, this is also where Curabone is crucial, because it's only possible through very advanced modeling. And that's what we've seen today. It's modeling, for instance, of tendons and ligaments in knee behavior or in jaws, trying to understand how bone is going to reheal after surgery, what the forces are, trying to understand how the implications of that are on the implant design, and trying to understand new approaches with porous implants and bone scaffolds. And also resorbable implants, which is yet another innovation for the future, where we need to understand how the resorption is going to be in the patient and how it compares to the natural restoration of the native dynamics. And as the last example that we've seen today, we are also working very hard on translating all of that research into our applications that reach hundreds of surgeons and thousands of patients every month. And so we're hoping with that to create a lot of benefit, which also this example shows. So it's not only benefit for researchers of having nice publications or companies of having nice business, but it's in the end, maybe most importantly, benefits of patients. And this is the example of a bioresorbable splint that helps babies with a collapsing air pipe from either suffocating or having to stay on a ventilator machine for 1 or 2 years of their life, which is a big toll on their personal development and on their family, of course. And this is also what we can only do with this type of very strong collaboration with universities and with young PhD students. So this fundamental research that is needed to make these innovations can be done together with academia. And this is also how we plan to continue in the future to help creating a better and healthier world. And so I want to thank very much all of the participants and all of the partners, and especially, of course, also the University of Zaragoza. Thanks a lot. And with that, I give the word back to Manu.
Okay, thank you very much, Koen. So I think now it's time for questions. I think Maria Angeles is managing all the questions.
Yes, we have a very nice questions, mainly a lot from Enrico de Lara from the University of Sheffield. So let's start with the questions. So the first question goes for David. So hi David, great work. Short question, when you optimize the position of the knee prosthesis, do you focus on the peak forces or on the whole curve? How are the differences pre and post virtual surgery in the peaks? So very good question, Enrico.
Yeah, indeed, it's a nice question. So in this project, we focus on the whole curve to try to find a position where the implant could replicate the whole native kinematics through a range of motion from 20 to 120 degrees of knee flexion. What Enrico proposes, I believe it's try to maybe to reduce the peak loads and so on. In this case, we focused on mainly on kinematics instead of forces, because that's what we could validate the musculoskeletal model, because we had kinematic measurements of so experimental kinematic measurements of the tibia, patella, and femur motion. So the second question, sorry, what was it? Yeah, so we can indeed see difference pre and post surgery. That's what I'm currently analyzing and trying to relate to the problems. It depends. So of course, the post-operative motion depends a lot on the shape of the implant, which I'm using right now. It's a cruciate retaining implant, which guides more or less the motion of the knee. So there's still a lot to research in that state, and there's many variables that we hope to take into account.
So thanks, David. So we have another question from Lisa McNamara. Thanks, Lisa, for attending and for making questions. So this question is for Gabriele. She says, this looks great. We really enjoyed having Gabriele in our lab at National University of Ireland in Galway. So based on your studies, Gabriele, what do you believe the outstanding challenges are in the area of microfluidic devices to ensure that they can represent the in vivo environment for studies of bone biology and disease?
Okay, yeah. Well, that's a great question. Based on what I saw in the literature, for bone tissue, we have, the development of bone on chips has been much slower than for other tissues. And of course, in other tissues, we can really see that the hydrogels, for example, used to describe the environment are really well developed, and even the interaction between different cell types. So of course, what I would really pay a lot of attention is, of course, the development and the choice of correct hydrogels for representing specific bone environments, because of course the microenvironment can definitely change even within the bone tissue, depending on the different disease you want to model, the different process you want to model. And then of course, the cell type would also be another key point. You need to choose the correct cells types for the process you want to model.
Okay, thank you, Gabriele. So there is another question from Enrico de Lara to Jonathan. So he says, a very nice application of finite element models for subject-specific implants. It's very difficult to validate the outputs of the finite element models for bone implant micromotions. We all know that. We are all aware of that problem. So with the collaborators in Canada, I understand that he and his team, we have used combination of in situ mechanical testing within micro-CT and digital volume correlation to validate the outputs of the finite element models for the shoulder bone. It may be worth investigating its application on implanted shoulders. So it's not a question, but it's a suggestion. So if you want to comment something, Jonathan.
I will just say thanks for the suggestion. It's indeed something challenging and a challenge that I had during the project. In K11, they have digital image correlation, and I also investigated the possibility to do that. Then because of time, I couldn't do, but I saw that the paper is quite recent. So it means that it's a hot topic also now. I will for sure read it and see if there are possibility for an application to the shoulder implants. Thanks for the question.
Thanks, Jonathan. So we have one question also for Antoine. From Enrico also. So he's asking, he says, masticatory loads can be pretty complex and maybe asymmetric. The beauty of your multi-scale approach is that it could predict implant tissue changes due to asymmetry of the load. Have you tested the effect of different possible loading conditions?
Yeah, that's a very interesting question. So yes, it's true that masticatory loads often aren't symmetric. For instance, in many studies, the bite force is taken at complete occlusion, so with both jaws completely in contact. But if you realize in everyday life, that's not what's happening here. When you're chewing something, you don't do it symmetrically. So the loading conditions I consider in this model is alternatively right and left molar clenching. So
numerically, it's in fact 1 day over 2, it's on one side. And it's also right, yes, with the appropriate bone healing model, it could be possible to see the tissue distribution, and even going further with the idea of doing bone remodeling. And yeah, it could be a nice application to this model, even if in this case I was focusing on the plates themselves, but there's also some interesting works that can be done in this direction.
Thank you, Antoine, for the answer. So there is a last question from Enrico to Gabriele. So, well, he says that he's very interested in the outputs of the mechanoregulation model that you have developed. And he says that in mice, they have shown that CT-based finite element models combined with remodeling models based purely on mechanoregulation predict well cortical bone apposition, but not so well resorption. So he's asking, how do your models predict local tissue changes? And did you see better predictions in some portions of the scaffold where the bone was more or less loaded?
Okay, yeah. Well, first of all, in our model, we were modeling bone regeneration, meaning that we didn't model any bone resorption in the model. Of course, this is an assumption. This is a pretty big assumption. But of course, that's another question, whether or not actually during the bone regeneration process, we have significant resorption also taking place. But this is something that I think should be first observed experimentally. And I'm not sure that we already know that. But yeah, as Enrico was suggesting, we noticed that basically we observed variations in the bone ingrowth distribution when for different implantation sites, and where the distribution wasn't homogeneous. So when it was heterogeneous and higher in the periosteal side, the variations in mechanical stimulus there was much higher. And there, yes, it was easier to actually track, to capture these variations. While when the mechanical stimulation was more uniform, like in the epiphyseal location, then it was a little bit more tricky, more difficult to get it.
Okay, thank you, Gabriele. So there are no more questions. There is an additional comment from Luca Cristofolini that thanks for the invitation to the Curabone final event. And I think there are no more questions. So thanks to all of you. And I give the floor again to Manu, so to close the event.
Okay, thank you very much for all of you, for your participation, your contribution. And okay, this final event has been finished. Thank you very much.
Bye.